Perfect. So, hi everybody. I'm Serge, and I make a living out of building or fixing or improving or packaging compilers. And I'm also a woodcraft lover, and it turns out I do all this stuff for the Red Hat company. So in terms of packaging, I'm more of a tinkerer than an engineer, but that's how it goes. And let's see what has been my trip in packaging LLVM for Fedora. Some would say that this talk is some kind of cathartic presentation because as many packager, I've been suffering for some times, and so sharing the pain is a good way to make it disappear. So we are talking about LLVM and packaging and Fedora. So let's start with Fedora. So Fedora is a Linux distribution which tries to be very close to the upstream release, at least for the rawhide release, which is roughly equivalent to what you can find in Debian seed. And otherwise, there are version releases that are much more stable, which are, for instance, F33, 34, 35, and 36, which is actually rawhide right now. It supports plenty of architecture, but some of them are tier 1 architecture, namely x86, only 64 bits, even though we support multi-arc there for 32 bits on 64 bits architecture, ARM 32 and ARM 64, PowerPC low Indian, Little Indian, and lower tier for RISC-V and MIPS. And the package used in Fedora's packaging system is RPM. So that's for Fedora, and it also has some guidelines that are quite strict or some that are not, which we tried hard to follow when packaging LLVM. This will be important later. And what is LLVM? You may not know anything about that. So that's a low-level virtual machine for the beginning. But you may know it through one of its front end, which is Clang or clang, depending on, I guess, the country you live in. And if clang or Clang doesn't ring a bell, maybe GCC does. So GCC is both a front end for the C language and a compiler infrastructure for building compiler for other language like G++ for C++, G Fortran for Fortran, etc. And so this compiler infrastructure for GCC in LLVM, it's actually called LLVM, and the front end is called Clang. So what is a compiler infrastructure? A compiler infrastructure is or can be designed as a set of roughly independent libraries. Some of them take care of the optimization of the internal representation of the compiler, like doing inlining or unrolling or constant propagation or whatever funny code optimization you may think of. But there is also a large set of backends. That is how you turn the internal representation of the compiler into actual machine code. And then there are satellites libraries that, for instance, advanced data types or system abstraction, because LLVM supports both Windows OS X and Linux. Some enhancement on the C++ standard template library and plenty of other stuff. There are also, not mentioned in this slide, but analysis that give you abstraction of the internal representation, like dominator trees or the call graphs, this kind of thing. So basically, LLVM, a very important piece of software to build compilers and at the core of Clang. So LLVM is also the name of the whole project, the LLVM project. And so at its core, there is the LLVM subproject. But then depending on it, you've got plenty of component, package, libraries pick the name you like. So we have a linker, LLD. We have a compiler runtime, granularity. We've got not machine learning internal representation, but multi-level internal representation, which is a higher level representation of what a compiler can do. And based on all this stuff, you can build compilers. So for instance, a Fortran compiler called Flang, which itself depends on pieces of the C compiler, or C, C++, and Objective-C compiler, which is clang. And based on clang and the LLVM, you can also have a debugger, which is lldb. And you also have a few relatively independent libraries like an equivalent of the standard std C++, which is libcxx, an implementation of the C++ standard library, and libunwind, which is an implementation of the system unwinder. So all these projects live within the LLVM project. And I did take the time to present them because one of the important parts of the LLVM project is that all these independent piece of software live in a monorepo. That's actually relatively new. For a long time, LLVM has been hosted on SVN, and then each of the components I presented in the previous slide had its own project. And through CMake machinery, we could have the component depending on each other, and everything was working fine. But at some point, the community decided to move to Git through a monorepo, and there are a lot of good arguments to do that, but I'm not going to expand on them. So we have a very huge monorepo. The release cycle is well structured. Every 6 months we have a major release. In between, we can have minor release, either to fix bugs or for security issues or to fix ABI issues. And for each release, we have several release candidates for testers to check. So as I already mentioned, the project is built based on CMake, and it's mostly C++ 14, but there is also non-negligible parts written in Python for mostly the tooling or scripts and this kind of stuff. So that's the LLVM project, and the remaining slide will be what kind of experience did we get when packaging this large software, and what other people could learn or at least get some interest in. So when packaging monorepo, we basically have two choices. And when doing the job for LLVM, we had to make a choice between either have one spec file or one recipe to build all the components from the Git monorepo. And that's actually very easy to do because that's the way it's done upstream. You configure your monorepo to build part of or all of the components, and they can depend on each other. And CMake is handling all this stuff automatically. So only one rule to rule them all, and that would be super easy. But if we choose that path, we spend something like 7 to 10 hours probably to rebuild everything, including the testing for all architecture. So if we need to patch one of the source for only one component, then we need to rebuild everything, and that's very costly in time, and so it breaks the nerves of the packagers, and especially when you're iterating and trying to understand a bug. So there is another path where instead of following the Git repo, we follow the upstream release, which are still made through independent tables. That is, every component is released as an independent tarball, which is basically a Git snapshot of the source. And then we unpack each of them in different spec file, in different recipe, and we check the dependency as any other package would do. Clang checks whether LLVM is available and use the existing headers and library to do its job. So the benefits of this traditional approach is that the recompilation is faster, so we can learn patch faster, make it evolve more easily. So that's a really big plus. But this way of building each component is somehow supported upstream, but it's not the current direction. So we need to be present upstream to keep this working. So it means basically more maintenance for the packagers. So we did choose option 2, which is actually the legacy approach, which is but still beneficial. But yeah, it means more job for the packager, but less pain when patching. Always a trade-off. Then we've got all this library. So we have libraries for LLVM, libraries for lldb, for LLD, for clang. And some of these library are mostly C++ code. And the community made the choice to not follow any API compatibility rule. That is, for every major release, we can break whatever contract we had with the customers. Why would we do so? That's actually very interesting. We do care about the customers of the library, but we want them to evolve with us. If we provide some kind of ABI compatibility, then it prevents the LLVM developer to make their library evolve in strong and maybe breaking ways, and it also makes the customers somehow lazy, because they would not try to update their dependency that much, because, well, the older libraries still work. So as we are a very optimist community striving to get better code, we provide no stability so that people need to evolve with us. But we still do care about some of them. And there is a C interface, which is a subset of the C++ API. And this one has a much more stable ABI across release. So that's actually an interesting approach. You can evolve as you want with a full API, but you keep a smaller, stable one for C. So when you're a client of the LLVM library, you either choose the C minimal interface or the C++ one. We are a compiler, and one funny thing compiler people like to do is bootstrapping. That is, compiling their own compiler with their own compiler or with another compiler. And then, recall that I mentioned the Fedora policy at the beginning. For a long time, GCC was the compiler of any C or C++ software of Fedora. And one needs a very strong motivation to bend that rule to use another compiler. They succeeded once for Firefox, because Firefox was mostly supporting Clang upstream, and the cost of maintaining the GCC builds was very high. Plus, there were Clang, but Clang didn't have enough security features. But we did the job, and so Clang was one of the few no, Firefox was one of the few projects built by Clang. But since then, the rules have evolved and we can choose which compiler to use. So using GCC, well, it's nice because it's a Fedora default compiler, so it's well tested on the distribution, and well, that's the default with everything that brings well with it. But at some point, we wanted to build LLVM with link time optimization, with LTO, and that build just failed. And you don't want to debug your compiler when building your compiler, right? The nice thing with Clang is that building LLVM and Clang with Clang is part of the official test suite somehow. So at least that's something upstream does a lot. So that was a possible choice. And one strong motivation for doing so is that the LTO build, at least with thin LTO, that is, well, that's one kind of link time optimization, builds totally correctly and fairly fast. So using Clang instead of GCC here was not just about, yeah, we are using our own compiler to compile our compiler, but also just having a more optimized build. So the minus point for doing so is it's recent, so we probably did not catch everything. The LTO build still fails for when building Clang with Clang, but not when building LLVM with Clang. So we are still mixing some GCC builds and Clang builds software, but the ABI is stable between the two, so it currently works correctly. But there are probably some edges, sharp edges there to fix still. Another interesting upstream policy of the LLVM project is that by default, static archive are used. Yeah, even in the 21st century, we use static archive. And the reason behind this is probably faster linking or less problem to deal with, as would Linus Torvald say. But remember Fedora policy? We need to use shared library. So without strong reason, we need to do the step. Another advantage of shared library, especially in the context of LLVM, is much better disk usage. We have a lot of utility tools bundled within the LLVM and Clang package, and sharing them as static library does significantly increase the size of the package, and not everyone leaves behind a fiber connection. So that's actually a very strong argument for using shared libraries, but it's not the default configuration upstream. So again, we need to make sure, so it's still a supported upstream configuration, but it's less well tested. And so sometimes it's for us packager to do the test and to apply the patch upstream and so forth. But well, that's done once and then it just works. So the advantage of static archive are just, it's the default. And so that's less work for us, but the disk usage is really too much. So here we picked the shared libraries. It does mean some extra work for the packagers, but yeah, that's why it's a job. Another interesting aspect is lllvm.iso is a super large shared library, like very, very large. And when doing the linking step, taking all the object code, putting them within this single library, it's actually very slow. Slow like memory swapping, or slow like more than several dozens of minutes. And we don't want that. We know that the build is going to be long, but if we can do something to make it a bit faster, let's try to do so. So the first reason why it's slow is because of the size, and there are a lot of debug info. So C++ does generate a lot of debug information. That's part of the language, so we should cope with that. But we can still decrease the quality of the debug information through the flag -G1. And in that case, we do produce the build faster. So that's one possible option that we chose. Another option is we do build in parallel, obviously, but sometimes too much parallelism makes the compiler swap, especially when compiling C++ would some C fans say, and well, somehow they are correct there. So what we do is we first build the LLVM library, only that one, which breaks parallelism. And during the linking step, we limit the parallelism to one job. So the goal here is, instead of having a very wide parallelism tree, we try to make it a bit deeper and less wide. So that's less parallelism, but less memory swapping. We could also use another linker than the default system linker. And as LLVM compiler infrastructure, LLVM project does provide its own linker, which is known to be super fast, LLD. We could use it. We are still not doing so. That's a possible option. But yeah,
So,
trying to.
Serge,
Yep,
you have 2 more minutes.
that's perfect because I have 2 more slides.
Awesome.
Up. And then another choice we made for LLVM is we don't ship several versions of the Clang compiler and of the LLVM library. Like there is no Clang 13 and Clang 12 and Clang 11 living at the same time in Fedora. So it makes the packaging easier, but it's not super fine for users of the LLVM libraries. So what we do is we still package only some core libraries as compat package with correct SO names. So we don't ship most of the binaries, but only some of the libraries that still need to be linked with by other packages that don't live strictly in the LLVM project. And we also use how do you call that? Symlinks to just make sure that there is some kind of abstraction for the library so that users don't need to depend on them. So that's update alternatives. And yeah, testing. So when testing individual package, we first run the unit testing that are bundled within the source. So that's it makes the build much longer, but that's minimal quality expected. And we also have a CI system within Fedora that tests the actual installation of the package. And for that, we developed with the Debian LLVM maintainer, Sylvestre Ledru, an integration test suite that is meant to be shared across distribution. And so we are using it just to check that all the package we build actually do what we expect them to do. And that's all for my presentation. So I leave you with the LLVM logo and the official pun about it that you can find on the LLVM project. And if you have any question, I'm open to them.
Thanks, Serge. Unfortunately, that's all the time we have for this broadcast.